Thank you. Right. So hello everyone. Thank you for coming to the session, Visual Feedback. I'm going to chairing the session. And for this session, we have 4 papers. The first paper, Study of Interface for Time Continuous Emotion Reporting, is going to be presented by Jason. Jason is a postdoc research scientist at the University of Louisiana at Lafayette. His research interests include physiological processing and medical applications of VR. Jason can start if you're ready.
Alrighty. All right, so like she said, my name's Jason, and I'll be talking about our work studying the interfaces for time continuous emotion reporting. So, as the title probably suggests, we are interested in looking at the ways that people report what emotions they're feeling. So, why might we be interested in that? Well, for one, we can build emotion recognition models from this. Emotion reporting is important for getting that ground truth data that we then train our data sets on, and we can use this from detecting bored or frustrated students in a VR classroom, or maybe dynamically adjusting gaming difficulty to prevent gamer rage or whatever. And we can also use it without training data for product design. So maybe we just want to get customer reactions to a product, or we want to see how viewers are responding to a video. You know, if a video is supposed to make them happy, does it actually make them sad, etc. The way we typically conduct this kind of emotion reporting is that we will subject them to a stimulus, 360 video maybe, and then we will have them report, filling out something like the self-assessment mannequin, and then we will extract from that an emotion that we think they felt that they've reported to us. And this is how it goes in most VR works that we've seen. But maybe, you know, another context will be nice. Say I'm interested in seeing your emotional reactions to this talk right now. Maybe I subject you to a stimulus, which is me talking at you, and then at the end I give you a card and you fill it out and I say, okay, you were excited, that's great. But as you might notice from this context, that doesn't really make a whole lot of sense, right? Because you're probably experiencing a whole range of emotions across the 12 minutes here. Maybe you start out sleepy because it's the morning, and then you get piqued by my use of metaphor, and then I start to lose you, and then at the end you come back and you're excited. If I just associate that with a singular reporting of excitement, then I'm losing out on a lot of the nuance that I could have been collecting throughout that. And if I'm trying to build an emotion recognition model, then a lot of my physiological data is just kind of not going to match up with that, right? We might just have to guess which part of the data is in line with that excited feeling and then trash the rest of it. But a solution is to just have them continuously report their emotion as they're going through the stimulus. Now this is not a super easy task, of course. You have to be thinking about your emotions as you are experiencing the stimulus, and you have to be thinking about how you're reporting. So giving people decent visual feedback is, of course, very important to let them know what they're telling the computer. So there have, of course, been prior approaches to solving this problem. Some people in psychology have had you maybe rotate a dial that's on a desktop and it shows you on a simple dial indicator. Maybe you give some input on a touchpad and it modulates the expression on a face, and hopefully your input is reflected and your face matches the face. But importantly, a lot of this work has just been done on desktop and doesn't take into account the design affordances and limitations of VR. The one work that we did find was a singular work called RCEA coming out with the Halo Light design, but we didn't find any real comparison of how these visual feedback interfaces stack up against each other and really what we might want to consider for such an interface. So with that, we laid out a few design requirements. So since we're aiming to have them report in real time, we of course want them to be able to use them fast. The interface has to be snappy. We want them to be precise because you're probably experiencing a similar emotion, so you want to be able to know that you're, reporting happy each time you report that you're happy. We want them to be non-invasive. We want to minimize the size, since especially if you're watching a 360 video, you don't want to obstruct any of that valuable screen space that you're looking at. And we want them, maybe most importantly, to be intuitive, because we already consider it a mentally complex task to experience a stimulus and then report on how you're feeling and think about the different dimensions of affect and such. So these are the sort of dimensions that we measure our results across. Okay, so we ended up with a whole range of visual feedback types and interfaces. Each of these is controlled by the user noting a valence and arousal report with their thumb on a Vive controller. If you have never heard those terms, valence is basically just a range from sad to happy. Arousal is basically a range from calm to excited. And then all of the spectrum of emotions fall somewhere within those dimensions. So we had two control schemes laid out, and then we wanted to test a pilot study. So we ran a pilot study with just these 5 that we had first, introducing a couple of continuous adaptations of popular former post hoc use ones. So, for example, the SAM method, they could slide their finger around and it would show them what arousal and valence they were reporting. Can't get into the results here, but you can see them in the paper. Essentially, we eliminated the SAM interface because people said it was too obtrusive. Because the nature of the design is that it's quite large, it took up too much of the screen. Similarly, the emoji grid was reported as not being responsive enough and conveying too much information as once, so we got rid of it. Then we iterated on our smiley design and came up with the following 4 interfaces that we compared in a test. So let's go through those now. So the halo light is the work from prior authors. This essentially shows a different color on a circle in the corner periphery of your view based on what quadrant of the arousal valence spectrum you're in. So say you're reporting high arousal, low valence, it would report red for something like angry. If you are doing high arousal, high valence, it would be yellow for something like excited. Now this is nice, it allows for one-handed controls and it's pretty simple, but we were worried that it's not precise enough. It does show intensity or distance from neutral with opacity, but there's no color change within a quadrant, so if you're arcing along, you're getting just the same color. Then we tried to address that by introducing the gradiated halo light. This just mixes the color of the 2 nearest quadrants based on the angle. So if you're going straight up, so high arousal, neutral valence, it would be orange instead of kind of flickering between yellow and red. We hope here that the addition of more colors makes it more precise, since you can know to aim for that orange if you're trying to report that kind of emotion. We kind of adapted the affect button interface into this simpler smile. So here we just have the valence adjust the mouth curve. So if it's high valence and you're happy, it's a little smiley face. If you're low valence and it's a frown, it's a frowny face. Then the arousal adjusts eyes, eyebrows, and saturation, all of those parameters being based on a secondary pilot study that we did just for this design. And then we had the 2-face smiley, which, like the 1-face smiley, is a smiley but with 2 faces. It separates the dimensions here, so the right face shows valence and the left face shows arousal. And we did this because while people didn't like that SAM was very large, they did like that it helped them mentally separate the 2 dimensions. So we figured this might be a simpler way of getting a same effect. Then we wanted to validate the usability of each of these interfaces and compare them across those metrics like we talked about earlier. So we had a 5-phase experiment design. We started with initial impressions. We just wanted to put them in VR, show them the interfaces, and then have them play around with the inputs and ask, what do you think this feedback means you're reporting? Then we wanted to send them through training. So we gave them a PowerPoint presentation on the arousal valence model, where they would attempt to rate 10 emotion words, all picked from some seminal work from Marium, and the proctor just corrected unusual responses, like if they gave high valence for depression or something like that. This was hopefully to get them used to the arousal valence model, because we've experienced problems in the past of people just not knowing what those terms mean. Then we sort of got into our main phase, which we call the label reporting. So subjects used each interface to provide a rating for 8 different emotions words, similar to that training exercise, just now using the interface. They repeated this set of 8 words 4 times per interface, with each word being chosen from a different position on the arousal valence spectrum. This is where most of our data comes from, because it provides the most stable across users, whereas if we were just using videos, then it might, the emotional response from the user might be different. Then we wanted, of course, for them to actually practice using the continuous rating interface in an actual application, like the video. So we sent them through 4 1-minute 360 videos from a Stanford data set from 2017, and had them rate their emotions continuously so they'd have some context for the questionnaire later. Then we had them rank each interface by its perceived ability to report emotional state, just dragging and dropping in VR. And then we had them do a pen and paper questionnaire for which one was the most intuitive, effective, invasive, etc. So to recap, the experiment design was a 4x8 within subjects with 4 interfaces and 8 emotions with 26 subjects. Okay. Now, if we look at the results here, where we plot the valence against the arousal for each of the interfaces and each emotion, we notice that there are some interactions shown between the interface and the emotion. Generally, these are clustered by type, so you might see that the face-based ones are kind of separate from the color-based ones. And we saw that the smiley group was generally showing a higher arousal for curious, but a lower arousal for angry. Now, if these were consistent differences, these could of course be adjusted by just some offset or something, but the fact that there are inconsistent differences suggests that there's a real difference between how people rate the emotion with each interface. Then we also wanted to look at how fast they were reporting with each interface. We again saw some interactions, saw that the halo light was generally the fastest one there, with the gradiated halo light being generally slower, probably because there's so many colors to pick from, except for angry for some reason. And we saw the interesting pattern that certain emotions took less time or different amounts of times to rate than other ones. So we wanted to look just across all emotions how long it was taking, and found the interesting result that there are actually differences in how long it takes to rate different emotions. So for example, happy was generally the fastest, whereas things like relaxed and curious generally took a good bit longer, on average 2 seconds longer. So you can imagine if you have training data, you might need to offset your physiological responses by a different amount for different types of emotion. Came up with 2 possible explanations for this. One is that the interfaces were just bad, always a possibility, but the more interesting one that we think is true is that certain emotions actually just take more processing time in the brain to report. Based on ranking, we generally saw that the gradiated halo light and the single-face smiley were liked the best. And because I'm running out of time, quick jump to the conclusions. So the most important thing was that we found that the rating interface does have an effect on how users rate certain emotions. So we can't simply give them any old interface and expect that they're going to rate their emotions consistently with each one. Within the ones that we compared, we saw that the halo light performs the fastest, but is generally not liked for its vagueness. In terms of the data, it's still fairly precise, but not liked, so mostly want to be used if the speed is paramount. The gradiated halo light and smiley ones that we introduced are generally preferred among the subjects, but individual differences were seen based on how they associate emotion with color and faces in that initial phase. And of course, future work should investigate the nature of time continuous emotion reporting, since it's a very hairy subject, as it turns out. And that's my time. Thank you for listening.
Thank you. Thank you for your awesome research. I have two quick questions. First, can you more explain about how you measure the rating time? And the second one is that can you explain more about each of the cognitive loads?
Yeah, so the rating time, simply during the label reporting phase, we would flash a emotion label on the screen, and then they would have to rate that emotion as if they were experiencing it. So maybe they report like a 1 valence, 9 arousal for angry, or something like that. We had them do that 4 times for each word, and then we took the median time of the latter 3, if that answers the question. What was the second one? It was on cognitive load?
Yeah, cognitive, or each measures cognitive load.
Yes, so that's not something we were able to get into in this research. It's something that we're trying to find out later with maybe a NASA TLX survey or something. But it's definitely, we definitely casually have noticed that it takes people a lot more time to think about arousal more than valence, because it's just not as a dimension that we're as used to thinking about. But we can talk after you have more.
Thank you for the presentation. I'm Gon Lee from University of South Australia. I understand your interface mainly focuses on valence and arousal, but
Yes.
Typically there is also another dimension for dominance. Do you have any ideas of how this could be extended into capturing that dominance dimension as well?
Yeah. So
Please, thank you.
The tricky thing with dominance is that it's a third dimension, obviously, and we're typically, if we want to use the touchpad, it's just a 2D rating system. Something like the affect button used the periphery to do sort of a mapping with the radius and dominance that was a little more complex. But I think in VR we have more affordances with actual 3D positioning. So one of our next works is going to be seeing if we can adjust that by having them report on the touchpad and then pull the controller in and out to adjust dominance. But for arousal valence, I mean, if the original author is to be believed, I think it accounts for 67-ish% of variance in emotion, so it's a generally good model to follow, anyway.
Thanks, Jason. So you also got a question online. So we are running out of time, so please respond to the question in Discord to
Sure.
Joe. Okay, so thank you very much for presentation. Our next talk is going to be online, given by Daniel. So Daniel is a PhD student at the University of South Australia. His research interests include leveraging portals and impossible spaces in virtual reality. And the talk is about adaptive portals.
Hi, my name is Daniel Ablett, and I'm from the University of South Australia. I'm here to present our paper, Adaptive Portals, Enhancing Virtual Reality Interaction Spaces with Real-Time Self-Adjusting Portals. Our interaction techniques are open source, and a link will be available at the end to the GitHub repository. My fellow authors are Dr. Andrew Cunningham, Dr. Gun A. Lee, and Professor Bruce H. Thomas, all of whom are also from the University of South Australia. Portals have emerged as an innovative solution to maximize physical space usage in virtual reality. They act as a bridge connecting two locations, transforming distant interactions into experiences that feel as immediate as those within arm's reach. When we discuss portals, the primary world refers to the environment that the user occupies, while the secondary world is the one accessible through the portal. The entry of a portal is the side in the primary world, while the exit is the side in the secondary world. In further analysis of our prior point and portal study results, we identified a pattern where users commonly placed portals short of intended targets. This cautious approach seemingly stems from users' desire to preserve visibility through portals, but results in placements that compromise interaction comfort. Automatically snapping portals closer to interaction targets would not solve the problem, as the visual context would be lost. The problem with VR portals is that their effectiveness hinges on their placement and size, for which there is no one-size-fits-all solution. We propose adaptive portals, that is, portals that use a collaboration of techniques to perform real-time adjustments to better meet the needs of their users. Here we present the initial suite of adaptive portal techniques, including AP reach with exit and entry strategies, AP bounds, and AP restriction. Our AP reach technique is designed to overcome physical limitations and improve reach into secondary worlds. By moving different sides of the portal according to the selected strategy, we bring the secondary world within closer proximity to the user. This adjustment allows users to interact with the secondary world more comfortably, reducing excessive reaching and discomfort. Moreover, it ensures users maintain a clearer visual context of their interactions within the portal, making distant interactions feel within arm's reach. Entry AP reach shifts the portal's entry towards the user, but is limited by the entry's proximity to the user's head. As the user reaches into the portal, the entry side moves evenly towards the user. This strategy emphasizes the secondary world by bringing it closer in its entirety at the cost of the primary world view. In contrast, exit AP reach shifts the portal's exit further into the secondary world, bypassing this limitation to an extent. This strategy does not affect the primary world view at the cost of potentially visually clipping the secondary world as the exit extends outwards. Both strategies effectively shrink the gap between the user and the object by moving the secondary world and consequently the object closer to the user. We also propose and evaluate an alternative to AP reach called Portal Hand Mapping Reach, or PH reach, which is inspired by hand redirection. It is functionally identical to AP reach, but instead of adjusting the portal to have the secondary world move closer to the user's hand itself is extended outwards. Like AP reach, PH reach accommodates any mapping, but given that portals inherently facilitate action at a distance, drastic mappings traditionally used by things like GoGo are unnecessary. Traditionally, when a user's hand moves outside the edge of a portal, it retracts back to the primary world, even when the user did not deliberately pull their hand out from the portal. To address this, we introduce AP bounds, which dynamically adjusts the portal to accommodate the user's lateral hand movements. When the user's hand reaches the buffer around the portal's edge, two possible responses are triggered: repositioning or stretching. In the repositioning strategy, the user effectively drags the portal along with their hand. In the stretching strategy, as shown in the video and used in the study, the portal expands to encapsulate the user's hand. We also found that users often accidentally teleported into the secondary world while reaching into portals. To prevent this, we developed AP restriction. When a user's head approaches a portal, the portal's entry is pushed away, preventing passage. The portal's exit mirrors this movement to keep the secondary world stationary. This thus gives the impression of entering a portal without the complications of actual teleportation. AP restriction also complements AP reach and PH reach. Normally, reach extension would be limited by the user's arm length or proximity to the portal, but AP restriction pushes both sides of the portal away, creating endless space for reach. We conducted a within-subjects user study to evaluate AP reach and PH reach, comparing the effects of adjusting different components, the entry, exit, or hand, for reach extension. AP bounds and AP restriction, being refinements of portal interaction, were included in all conditions for their necessity and to observe participants' utilizations of both techniques. To evaluate our portal reach extension techniques, we employed a 6 degree of freedom docking task, simulating direct manipulation activity. In every trial, a docking object appeared in one portal at random. Users had to grasp and move this object to match a corresponding semi-transparent target marker in another portal, as quickly and as accurately as they could using their preferred hand. Confirmation of placement was restricted until the docking object was within 10 centimeters of the target, ensuring the task was actually completed. The study used two independent variables, technique and distance. The evaluated techniques were the baseline with no reach extension, entry AP reach, exit AP reach, and PH reach. The docking object was placed at one of 4 distances during the trial. These distances were based on how far back users from our point and portal study placed portals from target objects. with the first three distances being common ones and D4 representing a more extreme, but less common case. Each user repeated each combination of techniques and distance 4 times. We found all reach extension techniques consistently required less physical movement than the baseline. However, the extent of reduced physical movement varied by distance, being negligible at D1 and most pronounced during the extreme case, D4. Given that all reach extension techniques employ the same mapping, it is not unexpected that there were no significant differences between them in terms of physical movement. Based on our analysis, we found exit AP reach emerged as the most effective portal reach extension technique. While the difference in user preference was not found to be significant, the preference ranking results showed a subtle yet notable inclination towards exit AP reach, with PH reach following closely, mirroring much of the performance results. We separated performance time into selection time and placement time. Selection time being the time taken to initially select the object, and placement time being the time taken to then move the selected object to the target portal and finalize its placement. We found that PH reach required significantly more time for object selection compared to all other techniques. This delay may be attributed to the difficulty users faced in seeing their hand with a docking object at further distances when using PH reach, whereas with the other techniques, the hand remained closer to the user's view. In terms of placement time, exit AP reach was significantly faster than all other techniques. However, this trend was less pronounced at the non-extreme distances, where placement times were generally quick regardless of the technique used. We found all reach extension techniques incurred significantly higher positional error than the baseline. However, it is important to note that the actual position error was relatively small across all techniques. For most practical purposes, where ultra-precise placement is not critical, these techniques are sufficiently accurate. All reach extension techniques significantly outperform the baseline in terms of effort, frustration, physical demand, and temporal demand. Exit AP reach further showed superiority over its entry counterpart and PH reach for reducing effort, frustration, and physical demand. The pronounced impact of physical demand findings compared to the actual physical movement measures suggests that visual cues of the techniques had a bigger impact on perceived exertion. We also monitored the usage of AP bounds and AP restriction throughout the study. While the trials were designed to be completed without it, AP bounds was triggered across all conditions. This usage highlights how prone to interruption portal interactions can be without AP bounds. AP restrictions usage highlights its necessity in preventing unintended teleportations during interactions. While AP restriction was heavily relied upon with the baseline, users rarely approached the portal closely when using reach extension techniques. With reach extension, AP restriction was generally only necessitated by the extreme case like D4, but is still effective nonetheless. In conclusion, we introduced the concept of adaptive portals through a suite of novel techniques: AP reach with entry and exit strategies, AP bounds, and AP restriction. We also presented PH reach as an alternative to AP reach for extending reach within portals. These techniques are all available via our open source Unity VR portal toolkit, accessible via the QR code on the screen. Our user study has revealed that among the techniques evaluated, exit AP reach stands out as the most effective in extending the user's reach. It significantly reduced physical movement, improved task completion time, particularly at greater distances. It was also found to lower effort, frustration, physical and temporal demand, and improve perceived performance. Our findings lay the groundwork for the future integration of adaptive portals in VR, providing empirical evidence that can guide developers in creating better VR experiences. Thank you.
Thank you, Daniel. Daniel is online in Zoom. Are there any questions from on site? Nope. I think if there's no question, and if the follow-up questions, you can always type on Discord, and I'm sure the authors will be there answering questions. So our next talk is going to be given by Marium on the topic exploring augmented reality user interface transition across mid-air, on-body, and physical surfaces. Marium is a PhD student in the Department of Computer Science at UBC. Her research interests include exploring and designing solutions to facilitate the use of augmented reality user interface across different media, on-body, and physical surfaces in diverse everyday scenarios.
Everyone, my name is Marium-E Jannat. I am a PhD student at the University of British Columbia. Today, I am going to present our work exploring augmented reality user interface transitions across media, on-body, and physical surfaces. My co-authors are Prateek Dhaka, Keiko Katsuragawa, and my advisor Khalad Hasan. Augmented reality head-mounted display offers users the potential for everyday interaction across different locations. Yet, the user interfaces in AR usually remain in media when users perform in-air gestures to interact with the content. This form of interaction lacks haptic feedback and leads to arm fatigue. However, on-body surfaces such as arms, which is always available to the users, and if any available physical surfaces around, like desk, can offer haptic feedback and reduce arm fatigue while interacting with the UI on the surface. We anticipate that the ability to move and place AR interfaces on arms and desk beside the media can provide more comfortable interaction for users in diverse public, private, and semi-private locations. Therefore, in this paper, we explore transitional user interfaces for augmented reality, where the interfaces can be moved between media, arm, and desk spaces with varying levels of control over that movement. To explore the concept of transitional user interfaces, we conducted two user studies. First, we conducted a study to explore the user preferences for placing AR interfaces on physical and on-body surfaces in addition to media across various everyday scenarios. To demonstrate the prospects of using arm, desk, and media as interaction space in diverse locations, we designed a set of 6 application scenarios where AR interfaces were used across private, public, and semi-private locations. For instance, here a user is using the bus transit schedule app in media and on their arm. This app is supposed to be used while waiting for the bus at the bus stand, which is a public place. Similarly, in this scenario, the user is assumed to review their daily task using the to-do list app when working at the office. And office is a semi-private location and all the spaces like media, arm, and desk are available for use here. In a similar way, we used these 4 other application scenarios too. A fitness tracking app during a morning workout at home, news app in a cafe, shopping list app while doing grocery shopping, and checking upcoming events at home. During the study, participants used all the applications and envisioned themselves using each interfaces in the corresponding locations mentioned in the application scenarios, such as the fitness app inside the home when they are alone and transit app in the bus station where there are other people around. We collected their preferences on each interaction space on a 5-point Likert scale, and through a semi-structured interview at the end of the session, we collected their subjective feedback and suggestions. Participants showed a strong preferences for using desk when they are available, and when a desk was not available, they preferred using their arm. Furthermore, in all the scenarios where a desk was available, the desk was the most preferred, followed by the arm, and media was the least preferred. In scenarios where there was no desk available, the arm was preferred over the media. However, in scenario 1, during a morning workout at home, users showed similar preferences for both media and arm. From the user feedback, we noticed a strong user preference for UI adaptation, particularly when UIs were on the arm. We also observed a need to transition UIs between media, on-body, and physical surfaces, as the participants mentioned that the ability to transition the UI between interaction spaces would be beneficial for them. Consequently, we conducted the second study to investigate methods with varying levels of automation for transitioning UIs between media, ARM, and desk. For this study, we designed and implemented three transitioning mechanisms: manual, semi-automatic, and automatic. In manual transition, users can grab the interface with a pinch gesture and manually drag and drop the interface on a space they want. In semi-automatic transitioning technique, the user can move the interface to the preferred space by tapping the button labeled with the corresponding space name. If a space is available for moving the UI, the button changes from red to green. In automatic transition, user interfaces automatically move between media, desk, and ARM based on their availability, where the desk surface precedes the other two spaces and the ARM takes precedence over the media. To examine these transitioning mechanisms, we used three application scenarios from Study 1. Transit schedule app to be used in a public location, news app in a private location, and event explorer app to be used in a semi-private location. Participants were taken to the actual public, private, and semi-private settings during this study. They were taken at the entrance of a busy academic building at the university as a public space. As a semi-private location, they were taken in a meeting room where there was one more person present except the experimenter and the participant, and in a private study room where there was no one else except the experimenter and the participant. Participants were asked to use the apps in the corresponding locations and transition between the corresponding surfaces for three mobility conditions, which is standing, walking, and seated. We collected users' preferences on each transition mechanisms on a 5-point Likert scale in terms of effectiveness, usability, workload, sense of agency, mobility conditions, and locations. Through a semi-structured interview at the end of the session, we collected their subjective feedback and suggestions. We used single ISMAR questionnaire to examine effectiveness and system usability scale for usability, and in both cases, semi-automatic technique was the most preferred one. Through NASA TLX, we noticed they perceived the least mental workload and frustration with semi-automatic technique, resulting in a better performance. Furthermore, we found that the participants felt more control and agency with the semi-automatic technique while transitioning the UIs between the interaction spaces. Consequently, they preferred semi-automatic transition for all the mobility conditions and locations with different privacy levels. During the semi-structured interviews, participants noted that the semi-automatic transition minimizes user interaction by eliminating the need for manual UI movement. They also mentioned it assists in decision making by showing the space availability while allowing full control over the transitioning process. Based on the findings from this research, we come up with a set with some design recommendations. We suggest that AR interfaces should transition from media to the user's arm or desk when such surfaces are available. We also recommend adapting the interface layout based on the input space size and area. And finally, we recommend users to consider using semi-automatic transition for moving AR interfaces as it offers balanced automation and user control for moving the interfaces. We believe the insights and design recommendations from this research will help in developing augmented reality systems in future for everyday application scenarios. Thank you.
Okay, thank you, Mariam. Any questions from outside audience? Yes. Mariam, are you online?
Yeah, I'm online. Can you hear me?
Hi, lovely presentation. This is Yue from Carnegie Mellon University. I'm wondering, so one of your key insights at the end was that the semi-automatic condition should be adopted as opposed to automatic. To what extent do you think that's a factor of the automatic condition misaligning with the user expectations, or is it like, is that something inherent to automatic adaptation, or is it more so a matter of the implementation not necessarily aligning with the user expectations?
Okay, so thank you for the question. It's a great question. I'm audible, right?
Yes, we can hear you.
Okay. Okay, so what we found, like during the interview at the end of the session, we also asked about why they did not like the automatic one that much, and the answer that we most received is like, it is automatic. It is not asking for the user's preferences. It is not asking for the user's permission if they want it or not. If it is available based on the prior settings, it is just automatically jumping on that surface. So what we understand that the users would like to have some sort of control over that movement, that yes, I want to move the UI from this space to that space. I just don't want it to be jumping automatically. So that's what we found. But yes, I agree that there like more exploration, more investigation is needed with different sort of automation maybe. So in this research, it is just the starting point. We are still working on that how the transitions can be more meaningful to the users, more comfortable. So it was just the starting point. We started with this type of automatic, that okay, we set up the precedence, what will be the most preferred, and the second one, the third one, and it was jumping automatically. And the lack of users mm, uh, users input or feedback that yes, I want it or not, that was the main concern for their like disliking that automatic thing.
Thank you.
Thank you.
Hello, thanks for the talk. Long term from ETH Zurich. So I'm wondering, have you also considered, for example, combining eye gaze information into selecting, so also with the semi and also the automatic methods? Yeah, thanks.
Okay, thank you for the question. So for this particular research, for this particular project, we did not consider it. We just considered some sort of semi-automatic thing where users' feedback will be accommodated, and also they can, there will be some sort of manual thing also. They can like click on the button, but we are working on that. We are working on like accommodating eye gaze, some sort of gestures, or maybe some sort of voice commands. And we have added those things in our future work section in the paper. And I would encourage everyone to go through the paper because we have written on the what are the like future directions, what other things can be added on top of that in the paper. And also our code base is available on the GitHub. The link is provided on the paper. So yeah, we are working on that.
Okay, thank you, Mariam. So thanks for the great talk. We're going to move to our next paper, which is also the last paper of the session, entitled Investigating Object Translation in Room-Scale Handheld Virtual Reality. It's going to be presented by Daniel and HAYOUN. Daniel is a PhD student in the College of Computing and Information Science at Cornell University, previously a master's student at the Department of Computer Science at Virginia Tech. His research interests include immersive collaboration and interaction. HAYOUN is a PhD student in the Graduate Department of Industrial and Systems Engineering at Virginia Tech. her research interests include virtual reality and human factors. Can we see the slide? Okay, great.
There you go. All right, thank you so much. So today I'm going to be presenting on investigating object translation in room scale handheld VR. So let me give you a little bit more about the background of why we decided to investigate this. So here's a YouTuber looking into an augmented reality application where he's playing around with this butterfly on a donut. However, when you look at him on the outside, you just see him waving around this donut, and he looks a little crazy almost. You can't really see what he's talking about. And over here, he's watching an immersive video. However, if you were to see him from the outside, you just see him staring around blankly. You don't know the context of what he's doing as an outside observer. This is very common in our research. As a researcher, we see a person in virtual reality, and we kind of see what they're seeing with their desktop display sometimes, right? But we don't really have access to understand the space around them, and now they're actually interacting within the space. So usually onlookers have both limited viewing capability and limited interaction within this domain. It also is particular in virtual reality that we exclude people who don't use an immersive system to investigate or to look upon what they're seeing immersively. So if you have eyesight issues, you experience VR sickness, maybe you're too young and the headset doesn't fit quite right, no matter what, like, we are excluding people that just do not use these headsets from viewing the immersive experience. So we've decided to create applications to allow people to use virtual reality environments through handheld mobile devices or handheld VR. So in this case, young learners are able to look at the solar system through scale using handheld virtual reality. Other works have analyzed and looked at the interactions that occur from mobile device users to VR users. Here's another example. So the key thing is that the virtual reality device is able to include a handheld device, and the handheld device can act as a window into the virtual reality environment. So for a little bit of background of what we decided to investigate, we really wanted to understand interaction for mobile devices. How do mobile devices interact with this immersive environment? VR interaction is relatively well understood. Whether or not you look at VR or AR head-mounted display interaction, it's very commonly analyzed in many interactions. However, handheld VR is relatively underexplored. We don't know whether or not it's similar to handheld AR, or maybe it's similar to a 2D game on your phone, because you are looking at a 3D interface, but using the 2D UI of the phone. There's also another problem in relation to space. A lot of handheld AR applications are at table scale, not room scale environments. When we look at immersive interactions, they typically encapsulate experiences that take up entire spaces around them, while mobile AR applications are typically focused on table or smaller scales. So this was kind of the design scope of the issue. So to understand handheld VR interactions, we decided to look at manipulation, specifically translation, given that it was a space-dependent task that required users to move around the mobile device to understand the space around them. We also want to understand how people interpreted UI. Was it a 2D game or a 3D game? And was it similar to handheld AR? As a result, we did a Fitts law comparison to analyze whether the interaction was 2D or 3D. So here's the application design. It was an object translation task. Move the object from point A to point B. Here is the environment. We use lots of cues to indicate space, such as shadows, and also distance, such as the 1 meter markings along the walls and the floor of the environment. Here's an example of one of our interfaces, 3D touch. We use a touch-based manipulation technique. It's a combination of 3D touch and slide AR to move the object along each independent axis that the user selects. So when the user selects an axis, they can move along the axis. Here's virtual grasp. They can grab onto the movable object by pressing a button on the UI. It becomes fixed to their device, and they can use a slider to increase or decrease the distance to and from the object, and the device. Here's joystick. This was inspired by a lot of 2D games. Whether or not you've played a game on your phone, such as Genshin Impact, you probably experienced joystick, even if you play like games on console, for example. So this is a very common interaction that we wanted to analyze as well. Now on to the user study.
All right, so in this study, we aim to answer 3 key research questions. So the first one was how do different manipulation methods and task conditions influence users' performance and behavior? And then second, how do these manipulation methods compare in terms of usability, workload, and preference? And lastly, how does the unique nature of Handheld VR with its 2-dimensional input system in a 3-dimensional task environment align with Fitts' law? So for the user study, we designed a simple translation task. In every trial, a red sphere appeared at a fixed starting point, and then the participants were required to move this object to a designated target. Our study used a full factorial within subject design. Along with the manipulation methods, participants performed the task varying in target sizes and distances. To address the first research question, we recorded the device's activity logs. We measured completion time, the percentage of time participants spent near the target area, and then the device's movement trajectory over time. For the second research question, participants rated each method's usability and workload after using them. And then at the end of the study, they ranked their preferences and chose which method was the easiest to learn, most intuitive, and most fun. We conducted the user study in 2 phases. So in the first phase, participants performed the task while remaining stationary at a fixed location. So this was designed to explore scenarios where users have mobility restrictions, such as sitting in a chair. It also allowed us to conduct theoretical analysis like Fitts' law. In the second phase, participants were encouraged to move freely. This simulated an open space environment where users could walk around while interacting with the virtual space. So aside from being stationary versus mobile, all the procedures and tasks were identical. So due to the time limits today, we'll be focusing on the manipulation, We'll be focusing on the manipulation methods. For the further details, please refer to our full paper. So to start with, we found that the joystick method was the fastest, while the 3D slide method was the slowest, regardless of whether the users could move or not. For fine-tuning, virtual grasp took the highest percentage of time near the target area, while 3D slide used the least. Again, this pattern was consistent across both mobility conditions. So in terms of usability, joystick scored the highest on both easiness to manipulate and easiness to understand. Now moving on to workload, virtual grasp was rated the most mentally and physically demanding. It required more effort, more frustration, and had the lowest satisfaction in performance. However, when participants were allowed to move, its ratings improved, though it still requires significant physical effort. Overall, joystick was the most preferred. But when participants could move, virtual grasp was almost equally favored. And we broke it down further and voted on what was the easiest to learn, most intuitive, and most fun, and joystick again received the most votes. But again, when participants could move, virtual grasp was much more favored, voted at the most intuitive and most fun. Finally, to address our third research question, we applied our data to Fitts' law and its extended models for 2D and 3D environments. And our results showed that the Chai-Myung's model, which incorporates 2 angular factors, provided the best fit for all manipulation methods. Now I'll hand it back to Daniel for discussion.
Thank you. So we noticed one key thing. There's a trade-off between speed and precision. This is a 3D slide where the people can interact with the movable object by selecting each individual axis. We said this had high precision because it had a high level of control, but it was slow because people had to select each individual axis. We also found that virtual grasp was also slow. People could move around all these different axes at the same time because they could move around their device, but it didn't have as much precision as 3D slide. However, joystick was able to have a combination of the two, being able to control multiple axes at the same time, but not too much. And we found that this trade-off led to a faster translation. Another thing that we noticed was that participants didn't really want to move. Given the ability to move around in User Study 2, most participants chose to stay in place. They didn't really use the space around them to try to understand and see how far the object was. if they thought that they could do the translation from where they were and when they started, they would typically do it in this starting position. Another thing we noticed was that device-based movement for the translation task was fatiguing. So translations are based on the device movement to have and perform the translation were fatiguing, but they were less fatiguing when participants were able to walk around and more understandable when participants were able to walk around. Another thing we noticed and wanted to point out was this 2D manipulation or 3D manipulation? We followed that the handheld VR follows Fitts law 3D environments as opposed to 2D environments. So people understand this as 3D space as opposed to 2D UI space of the screen. So to conclude, one of the limitations of this experiment was we did not perform a comparison of handheld AR and MR. So we tried to extrapolate some of the designs from AR to be in the mixed reality system. However, what study could be used to extrapolate these effects more clearly. We also fixed the handedness of the UI. Different UI could, of course, have different effects on the results. We could also explore different types of interaction, such as rotation and scaling, or to actually investigate other types of tasks. We could do non-manipulation-based tasks as well. The contributions of this was it allowed people to integrate handheld immersive spectator systems to actually be more interactive with the immersive experience of head-mounted display users. These design insights talk about how to include these handheld devices into your potential research or applications where you want to integrate other people that aren't allowed to or may not be able to use head-mounted display into the immersive environment. We discussed the implications between design, between device-based and touch-based techniques, and we discussed manipulation within this domain and whether or not users were able or not able to walk. So thank you so much. Please scan this QR code if you want to read more about our paper.
Thank you, Daniel and Hasan. Questions?
Thank you very much. Bruce Thomas, University of South Australia. Very, very nice talk and very good work. Was the head tracked relative to the display?
The display was tracked. It was as if it was a window into the VR environment. So wherever the device moved, it would move around like it was a camera into the VR world.
Because in the AR world with AR tracking, if you track the person's head, you get a better proprioception of where you are in the physical world. And when I looked at I couldn't tell from your images, but it didn't look like the floor was matched up with the physical floor.
We did match up the floor. The height was accurate, so if you wanted to lower the device down to the floor, it would be as if you were on the floor of the
It's
VR.
an angle thing.
Yeah. The angles aren't persisted between the head of the VR or the head of the user and the
Yeah,
device.
you might want to think about doing that, whether you get a better sense of connecting because you're connecting the physical world. It isn't AR, but you can see the corners of the wall coming down to the floor.
Yeah, definitely consideration for future work.
Okay, thank you very much.
Thank you.
Hi, thanks for the talk. Mitchell Norman's University of South Australia as well. I was just wondering, sort of in just generally where you're thinking these interactions could go in the future. I can see an avenue for eye gaze interactions to be a really interesting avenue to go down for this kind of tablet-based view into the world. So just your thoughts on it.
Yeah, I definitely think the place where it stands the most potential to be used is in augmented reality applications. If you're using, let's say, for example, like the Orion glasses out in the public, for example, if you want your friend to view what you're viewing, then you can make them use their device and see that application. So a lot of it is providing outsiders contextualization of what's happening in the immersive display. Yeah, so it's just providing interaction to and from head-mounted display users and non-head-mounted display users. So any interaction, whether it be you want to play with your friend, simple games such as like ping pong, you can play using your phone, or if you want to interact and teach someone, like let's say a teacher is using the handheld device, they can provide mobile display interactions to give the user, give the student in the head-mounted display unique interactions or stuff to do, such as assignments or tasks with the handheld device.
I actually have two questions. One is about clarification. So could you please provide more details about the participant demographics? Because I feel like the result seems like the joystick has the best performance in terms of various aspects. Is it because they're gamers, they're familiar with games, so it outperforms the others? The other question is about, I know right now it's about translation only. What do you think, if the rotation, say for example, is incorporated in the manipulation later?
So for the first question, we did survey the participants before they start anything, whether how much they have experience with mobile VRs or mobile gaming in general on their phones. And for both phase 1 and 2, we pretty much had a similar average score around like out of 1 to 8, we had about in the middle, like 4 or 5. So I think there was some segmentations between participants who were like very heavy gamers and who are not, and there weren't significantly any difference between the two necessarily across both phases, but we did want to explore further for future work how their experience, the level of expertise in mobile VR or mobile games would affect the results.
Yeah, it's definitely more intuitive to use because of the joystick. What was the other question?
Translation and rotation.
Oh, right. So one of the reasons we chose not to directly investigate rotation in the first place was because we felt it was very similar in terms of space. That the spatial complexity of the task would remain similar, whether it was at a table scale or room scale environment. So that's why we didn't decide to do it, but we definitely think it's very applicable given that it's a larger space. You might not be able to view the rotation of the object itself, given the distance. We think this is similar to many other mobile AR papers that have done rotation at a larger scale. But in terms of how it would change, it would just be more difficult to do rotation given that it is further away, so you might have less visual acuity for the rotation cues and you might be less accurate.
Thank you. So I guess that concludes this session. Thank you very much. Thanks to all the speakers, and thank you for the audience.